Hello, I'm David D. Hilster. I'm part of the HPCC Systems platform team, and I'm here with Ashton Williamson, and we're going to be talking about the NLP++ and processing medical text. First, I'm going to give you an intro to the medical text processing field. The current state of medical text processing really is that in universities, they're using very sparse and fixed training sets. They're very limited. And one of the reasons they're limited is because, of course, HIPAA has restrictions on getting data from real people. And of course, that makes there's a lack of human-generated test responses because of that. And so the sparse and fixed training sets is a big problem. Machine learning and neural networks are being used in this area a lot, but they're not used in industry because of their accuracy, and they're really not traceable, meaning when they have a problem with it, you can't really go back and find out why it's doing something right or wrong. In industry, if you look at what Ashton has found in part of his research, is that pretty much in industry, we have human beings reading the text and assigning codes. There are no real computer systems out there doing it. And even when humans do it, they are only up to 50% on their accuracy a lot of times, which is not a very good accuracy record. As for the digital human reader we're looking at today that Ashton will be presenting for medical tests, we're in phase one where we're really looking at the words in the medical codes, and we're matching those to text as a human would do, in this case, as Ashton would do. A second phase would be using more synonyms, more variations of words so that we would be able to pick up more things in the text. As we know, text can have a lot of variations. And in the third phase, which would be the final phase, the full-blown package would be to build knowledge bases for codes, for medical knowledge, the human body, and then to parse the medical text using more linguistic and medical knowledge. That would be really a third stage in this process. The advantages of NLP++ over machine learning and neural networks is machine learning and neural networks, they require large numbers of training sets. And of course, that's simply not available given the HIPAA restrictions. And NLP++ can be developed on a small set of data using humans' ability to generalize. So we can develop on a very small set, but make analyzers that will cover large sets of text without ever having seen them before. Of course, machine learning and neural networks can't justify or explain the results, whereas NLP++ is 100% code and can show you every step along the way. And training machine learning and neural networks creates a large carbon footprint. Some of these processes can run for hours and maybe even days to generate something that they can use, whereas NLP++ is a very small carbon footprint. There's no large training data set needed. The advantages over human beings, of course, human beings can't reliably remember tens of thousands of codes. Doesn't matter how much they're trained, but if you're dealing with 30,000 codes, human memory is not that great at times. And of course, NLP++ is a computer, so it has 100% reliable memory for large numbers of codes and terms. It won't forget, obviously. And of course, human beings do tire and make mental mistakes. And that's obviously not true with NLP++ because it is a computer language. So today we're going to be listening to Ashton Williamson, who has been working on this with NLP++ to process medical data. He's a master's student at Clemson University. He's got his Bachelor of Science in Computer Science from Clemson. He's under the tutelage of Dr. Amy Apon and Dr. Nina Hobig, and he's been advised by myself and Amnon Myers. We are the architects of NLP++, and he has been involved in other internships in a capstone data science project. Right now, he's working on a grant from the LexisNexis and HPC systems. And he's working on processing those medical texts using NLP++ and comparing those results to machine learning and neural networks. He has done an immense amount of work on this project. It is quite remarkable. For one person to do what he's done, it's really probably more of the work of three people. And I would like to make a little comment about Ashton's implementation. NLP++ is different from other computer languages because computer languages require you to think like that computer language and the computer itself. Whereas NLP++, you really have to think, how do humans do this a task? How do humans read text and assign medical codes? So Ashton really did an intensive study of the medical codes and all the corresponding ontologies using visual text, which is part of the NLP++ technology. He did say it was really invaluable or perhaps even impossible to do without visual text. The amount of text that he's looked at and the codes is really just tremendous. And visual text really helped a lot in that. Ashton is also looking at the words that make up the codes, and that, as what we can see in the literature, is really the first time someone has done this. The answer set is also interesting because we're using the answer set everybody else is using, and the results are, we're assuming that the answers or codes for the text are correct. We've also known, I've known over the last 40 years in NLP, when we had people generate answer keys for us, oftentimes those answer keys are not always reliable. So we are assuming those answers are correct. It could be that Ashton's method of doing it and finding the answers are really better than even the answer set, because again, answer sets oftentimes have errors themselves. And more important is that Ashton can clearly show justifications for the codes he finds. No one has done this job or type of processing on medical text before. So without further ado, I'd like to hand it over to Ashton, and he'll tell you about what he's done. It's an amazing project. Take it away, Ashton.
Thanks, David. I'm going to talk a little bit about our approach to medical code processing with NLP++. I'm going to give an overview of the background of the problem, our approach to handling the problem, and a little bit of discussion of the results that we've achieved so far. So, broadly speaking, medical coding is the task of assigning codes to patient health records. It's a complex task that requires abstraction or summarization of multimodal medical data. This includes free text data, tabular data, but its effects are wide-ranging. So one of the applications of medical coding is billing and claims processing, of course, but it's also used for record keeping and patient care and general medical statistical analysis. So it's an important task. Some of the common coding systems in use are ICD, the International Classification of Diseases. We also have CPT and HPCS. ICD is the one that we have targeted specifically. It gives us kind of a common language for reporting and monitoring diseases. So ICD has about 17,000 unique codes, which makes it a very challenging problem. The newest version, ICD-10, has even more at 140,000 unique codes. On the right, we can see an example of a code. We have a unique alphanumeric identifier, a letter followed by 3 digits, and then following digit. This particular example is accident involving animal being ridden, injuring occupant of streetcar. And it's built as an ontology. So you have a parent level classification, external causes of injury and poisoning codes. Then you have a more granular category, other road vehicle accidents, and then a specific class, so accident involving animal being ridden. So there's some amount of structure in these codes, but it doesn't get too deep. The data set we looked at in particular was MIMIC3. MIMIC stands for multimedia care, for multimedia intensive care, a de-identified database of electronic health record data. It contains 50,000 distinct hospital admissions, and it contains ICD-9 codes corresponding to each admission. It's openly available for research use, so we're able to get easy access and a large amount of data. The nice thing about MIMIC3 is that there's a lot of research that's been done into this database. so we can compare our results to existing approaches. So our thesis statement is this: can we design a system to assign ICD codes to medical notes that competes with existing state-of-the-art approaches while providing efficiency and explainability and functions in the absence of training data? I want to give a broad overview of our implementation to solving this. There's a lot going on in this flowchart, but the key characteristics are a pre-processing stage, a note processing stage, and then a post-processing stage. At the pre-processing stage, we do two things. First, we pre-process the mimic data. That includes extracting target notes, cleaning up text as necessary, and then writing to file. The other part of this is medical ontology integration, which we'll talk more about in a second. But this includes building knowledge bases for use within NLP++ that leverage pre-existing medical knowledge. The third part of this is note processing. This is the main processing step, and this is a part which NLP++ makes easy to run in parallel, depending on your available resources. Post-processing is a step that's particular to our approach and our necessity to compare to existing state-of-the-art approaches to medical coding in the mimic dataset. We'll take a look at each of these in more detail here in a second. So the first part of the pre-processing stage is generating our splits. So there are two subsections or splits of the mimic dataset that we took a look at in particular. One is the top split and the other is the rare split. So the top split includes the 50 most frequently assigned ICD-9 codes. The top split gives us an easier subset to work with because one, there are fewer codes. There are 50 compared to over 8,000. But also it gives us a smaller subset of notes. So it provides kind of a smaller subset of the problem while still giving us a significant amount of data to work with. This was designed to be easier to approach for some deep learning models that struggle with classification of a large number of labels. So the other split's the rare split, and this split's interesting because there exists very little training data for it. So these are the 50 least frequently assigned ICD-9 codes. That totals to 249 notes overall and 142 notes in the test set. And some of these codes appear very infrequently or not at all in the train set. So the second part of this pre-processing stage is leveraging medical knowledge. UMLS includes a repository of biomedical vocabularies developed by the U.S. National Library of Medicine. That includes the Metathesaurus, the Specialist Lexicon, and the Semantic Network. The Specialist Lexicon was particularly important to our project because we wanted to be able to handle variation in medical text, whether it's spelling variations, esoteric abbreviations or acronyms, normalizations or conjugations. Each term in the lexicon is assigned a unique entry identifier, which maps many different variants to a single base term, which makes handling variation a little bit easier. The next step of the implementation is designing these knowledge bases. So we want to take these EUIs and leverage them to extract relevant terms in the text. And we've done this in a few different steps. So we start by taking our target ICD titles. So this is the unique string attached to an ICD code. We then pull out important keywords that map to an entry unique identifier in the specialist lexicon. So this would include terms like acute post-hemorrhagic anemia, post-hemorrhagic, acute, or just anemia. From these, we generate a list of variants. These are possible terms that could be included within a title that map to a specific subterm with a unique entry identifier. Leveraging this knowledge base, we're able to tag words in the text. This is a small overview of the larger system that we've implemented that gives an idea of the flow of the process of predicting codes for a particular note. So the first step is using our dictionary and NLP++ to identify these variants and map them to a specific entry unique identifier. Once we've done that, we can separate the text into individual sections and subsections so we can get a more granular approach to identifying particular codes instead of predicting codes for an entire node. Once we've extracted these codes, we need to rank them. So we assign ranks according to confidence of their appearance within the note, which outputs usually rather large set of codes for a note, which we can then filter out to get a set of codes for prediction. That occurs in the post-processing step. So one of the approaches we've taken to activating codes, if you will, is taking all predictions above the mean weight. So if we have a set of codes like the one on the right, we would find the normalized mean of that set of codes and then take all predictions that are ranked higher than that. It's a simple approach, but it leads to very reasonable results. To process final metrics, we take a look at several different metrics. One of these is F1 score, which is just the harmonic mean of precision and recall. A 0 would be very poor precision recall. 1.0 would be perfect precision and recall. So the receiver operating characteristic area under the curve is the second metric we took a look at. This is a widely reported metric in the literature, and it's very nuanced, but it doesn't require a deep understanding to interpret the results. It basically gives us an indication of how well our classifier is performing on the target data set. So a 1.0 would be a perfect classifier, a 0.5 would be random chance. Precision at K is an interesting metric. It tells us how many of our K highest scored codes are present in the ground labels, which is useful particularly for information retrieval. So these are the results in the top 50 test set. Again, the top 50 set is intended to be an easier subset of mimic for existing statistical and deep learning approaches to the problem. Our approach is a little bit behind on this subset with a ROC-AUC, receiver operating characteristic area under the curve, macro averaged of 67.25 and micro averaged of 77.8. Again, F1 is a little bit lower than existing state-of-the-art with macro F1 of 33.63 and micro F1 of 22.12. Again, the same case with precision at K, for which we have 31.32. Where our analyzer, our approach exceeds the state of the art is when it comes to the rare 50 test set. And again, this is the set of the least 50 frequently assigned codes. So it's more of a challenge for existing deep learning approaches that require large amounts of training data. So we can see we are right in line with the existing state-of-the-art, the kept longformer, the fine-tuned version, which has a macro ROC-AUC of 82.7 and a micro ROC-AUC of 83.3, whereas we're at 80.01 and 77.8 respectively. Similarly, in F1 score, our approach returns a macro average F1 of 33.63 compared to 30.4 for the kept long former, and then 22.12 micro averaged F1 compared to 32.6 for kept long former. So if we take a look on the left here at setting, we'll see pre-trained, fine-tuned, and zero shot. So both of these, MSMN and kept long former, are deep learning models based off of deep learning models. So they take a transformer-based model that's been trained on a large amount of text, and they additionally fine-tune it to the problem. And they get decent results, but the key idea here is that these approaches require excessively large amounts of training data, which is oftentimes infeasible or challenging to aggregate. So our approach performs in the absence of any training data and still achieves relatively similar results, which is supports the idea that there are alternative methods out there for predicting medical codes that don't require large data sets. So another advantage to our approach is explainability and transparency. So compared to deep learning models, our approach provides selections from the document that support an individual code assignment. They're also traceable and human interpretable. So you can walk back through the algorithm for assigning code predictions and understand, change, or interpret these steps. The next part of this is adaptability and accessibility. So if you run into a challenge with your deep learning model at assigning medical codes, it's very challenging to adapt it or change it to address a particular problem. But fortunately in NLP++, we can build upon our existing approach to adapt to any situation, which makes it very transportable and very accessible. Not only that, but we also have a lot of work still left to do. There's a long way to go to perfect the system, and we've only done a small part of it. So another part of this, which we talked about a little bit, is that it's effective in the absence of training data. So by leveraging existing biomedical knowledge bases in tandem with information contained within ICD titles, we can build a performance system, and we don't need a massive training data set. It also allows for competitive performance in a zero-shot setting, as evidenced by performance on the rare 50 split. So I hope that was a pretty good overview of the approach we've taken to this, and generally supports the idea that there are approaches that don't require large training data sets that can be performant and can address these challenges without the requirement for these data sets. So we'd like to acknowledge the generous support from HPCC Systems for this work. Computations were executed on the Clemson Palmetto supercomputer that is funded in part by NSF MRI 2018069. And there's a list of references for further reading if you're interested in looking a little bit deeper into this. Thank you.